This is 5.5, Exponential and Logarithmic Models. The purpose of this section is to show you some real-world examples of where the things we've been learning can be applied. So things like exponential growth. This is a common type of equation that you might see if you're talking about like the growth of a virus or bacteria in a petri dish, or even population growth to a certain extent. Exponential decay would be if you were doing like carbon dating of something, you want to figure out how old it is, you would measure how much carbon is in there, and it will decay at a measurable rate to be able to tell you how much time has gone by. So these are very similar to each other. The main difference here is that this one has a positive value for b, and this one technically has a negative value for b. I know it says b is greater than 0, but has a negative sign in front. And that's just the way our book lays that out. There's some other ones that we're not necessarily going to do, but you often hear, like when you take the SAT or the ACT test, or if your class that does grades on a curve, so they call it, that would be this type of curve here, where the middle 50% is within this area, and then 25% is over here, 25% is over here, and so forth. But this is the type of bell curve that you end up, is what it's also called. So it's used in statistics a lot to figure out the median and standard deviation and things like that. So when you get into a stats class, you're going to be dealing with something that looks a little bit more like that. But we won't be dealing with that in here. Logistic growth. This could be something like if you are learning how to do something new, like typing, for example. Even if you don't type at all, you're not typing less than 0 words per minute, and then as you start learning to type, you get better and better at it. But physically, you can only get so good at typing, and you're not going to be able to get any faster. Like, you're never going to be able to type 1,000 words per minute. And so this starts off fairly flat at 0, and it increases for a while, but then it kind of levels off. So it has actually 2 horizontal asymptotes here that it stays in between. So again, logistical growth is where that is used. Not in this class, but that is something that does involve a variable up in an exponent. You had a problem in section 5.4, I think, that had a variable down here like this, and you had to be able to solve for it. So you may run into things like that in the future, depending on what you decide to study. Then you have like logarithmic growth, which could be something, again, like the population of the deer in the area, or rabbits, or something like that, or in maybe my neighborhood, squirrels. I've got so many squirrels around my neighborhood, and when I first moved in 20 years ago, there were like no squirrels anywhere. But squirrels came in and they started populating the area quite rapidly. But then eventually it is going to level off because you have limited space, you have limited food, things like that. And so it's going to eventually level off and have a natural kind of leveling off going on here. But that would be an example of logarithmic growth of something. So let's get into a few examples. So this says if you invest $1,000 at 3.5% APR, that's annual percentage rate, and the interest is compounded continuously, find how long it will take for your money to double. Okay, so you need to, first of all, know what formula that you should be using for this. It says compounded continuously. So as soon as I see compounded continuously, I'm thinking, okay, that is A equals P times E to the RT power. So that's what I'm going to be using. Now, in this case, they actually tell me how much I invest. And it wants me to double my money. Now, I'm going to show you that it doesn't really matter if they don't give you an initial amount and they want you to double your money, triple your money, quadruple your money. You can start with a number in there, or you can actually go to the second step that I'm going to show you right off the bat by knowing what you want to do with your money, double, triple, quadruple, and so forth. Because if you're doubling your money, then that means the amount that's going to be in there after whatever amount of time is going to be $2,000, because the initial amount is $1,000. So this is the initial amount, and this is double. So I put 2,000 here. If it said triple, I'd put 3,000. If it said quadruple, I'd put 4,000. And then I have E to my percent rate is 0.035, and then times T. Now this is what I was talking about. since I'm doubling my money, the first thing I'm going to do is divide by 1,000. And what you're going to see is that this side is just going to become 2. So you get 2 equals e to the 0.035 t power. If you're tripling your money, that would be a 3 there, because you'd have 1,000 and 3,000. Or if you had 1,000,000, it'd be 3,000,000. Okay? A quadrillion, it'd be 3 quadrillion if you're tripling your money. So it doesn't matter. That ratio is always going to end up being whatever this is. So since it's double, it's 2. If it's triple, that'd be a 3, and so forth. So you can actually skip right to that point. Now, I need to get this variable out of this exponent. So I'm going to change this, take the exponent, and I'm going to, remember, I'm taking base to the power equals n. I'm transforming that into log base b of n is equal to that power. So I can take that exponent by doing log base, whatever this base is, which is base e of 2. So 0.035t equals the natural log of 2. And then, so then to solve for t, I just divide by 0.035. So the exact answer is the natural log of 2 over 0.035. But that doesn't really make a whole lot of sense to leave an answer like that. You know, this is where we have an example of why you'd want to get an approximate solution. Because if I told somebody it would take them the natural log of 2 divided by 0.035 years to double their money, they'd be like, I don't know how long that is. So we need to have an idea of what that actually is. So you grab your calculator and you take the natural log of 2 divided by 0.035, and that comes out to be approximately 19.8 years. So this is a time when it's appropriate to approximate my solution. So exact answer, approximate answer. Second one, $500 is what I'm investing. So that's the value for P. We want to have this amount, A, after 10 years, T. So in this case, I'm looking for the rate. So what rate? I don't know that part. So again, I take 1,505 equals 500 times e to the 10r power. So I'm going to divide by 500, always getting the whatever the power is by itself first. So this is going to be 3.01, I believe, equals e to the 10r power. Like the last problem, I have this in this form. I want to transform it into logarithmic form. That's what allows me to get the variable out of the exponent. So 10r is going to be equal to log base e, so natural log, of 3.01. Divide by 10, and this is going to give me my rate. Okay, this is the exact value, but you grab a calculator, and it's going to come out to be 0.11, or that would be 11%. So I think I will pause there, and then I will pick up from there for the next video.